Let us now talk about recursive Java implementation for searching a key. In this implementation, we are considering this class for representing a node of a BST. We have key and left and right references, and this is the constructor of this class. In the recursive code, the idea is simple. If you are searching a value x in the BST, and if the BST itself is null, then you need to return false. This not only handles the case when somebody passes an empty tree explicitly, it also handles the base cases. Suppose you search for something like 19 here, you will come here, then you will come here, then you will end up with a null tree, right? You will recursively call for null. So this is also handled, and if somebody passes explicitly a null, that is also handled, because if you come here with a null, you will end up accessing null.key, which will cause null pointer exception. So this condition does both the tasks. If somebody passes a null, simply return false, because a key cannot be present in an empty tree. Now we check the given search x with the root.key. If it matches with root itself, then we return true. And if the root.key is smaller, suppose you are searching for 25 and this is 15, you know for sure this cannot be on the left side, you need to search for the right side. So if x is greater, you go to the right side. And this part comes only when x is smaller. So for this case, you go to the left side. So this is the recursive code for searching a key in a BST. Let us now talk about iterative Java implementation. In this implementation, we set our root reference to here. We compare the values of x with the root's key, and if it matches, we return true. If it is greater, we go to the right side. If it is smaller, then we go to the left side. We keep on changing the root reference in a loop. And we come out of the loop in two conditions. When root becomes null, so if root becomes null and if you come out of the loop, you return false. You don't have the x present in your BST. The other case where we come out of the loop is when root.key matches the x. In this case, we not only come out of the loop, we also come out of the function. We come out of the function and return true. In other cases, we simply decide whether we need to change the reference to right or left according to the comparison result. We have talked about recursive and iterative implementations of BST search. Now, what is the time complexity of these operations and how much auxiliary space they require? So if you look at this search function, it goes across the height. Suppose you are searching for 16, you will come here, then you will come here, then you will come here, right? And that's the maximum time it's going to take. Because what might happen is you're searching for 15, it's presented the root itself, right? In this case, it just takes the constant time. So the worst case time taken by any search is equal to height of the BST. If you're suppose searching for something like 19, then you will come here, then you will come here, then you will come here, and then you will decide that's not present. So that's also maximized by or upper limited by height. If you're searching for something like, say, 15.5, then you will come here, then you will come here, then you will come here, and then you will come here, and then you will decide that it's not present. So you're traversing exactly one extra than height, right? So its time complexity can be written as big O of h. Please note that I'm using big O, not theta, because h is an upper bound. It is at most h plus 1 comparisons. And it can be constant work also if it's present at the root only. So that's the time complexity for both recursive and iterative implementations, because the logic for both of them is same. They traverse across the height. So time complexity is big O of h. Now let's talk about auxiliary space. If you talk about recursive implementation, it requires auxiliary space for function call stack. And how many functions can be there in the function call stack? Let's see. Suppose you are searching for 16. This will begin and it will be there in the function call stack. It will call for the right, then it will call for the left, it will call for the left. So when you're here, all these functions are there in the function call stack. So auxiliary space required by the recursive implementation is big O of h. And how much auxiliary space is required by the iterative implementation? The iterative implementation does not require any auxiliary space. It works in constant auxiliary space because it's simply running a loop. So obviously, iterative implementation is better than recursive implementation because it does not require auxiliary space. Also, it does not involve extra function call overhead. Now, one last note about the search function. It is upper bounded by height. And if you have a binary search tree which is not balanced, it can become n. The height can become n. Suppose you are searching in this order. First you inserted 10, then you inserted 12, then you inserted 14, then you inserted 16. So height is actually equal to the number of nodes. So height can become n if your tree is skewed, if it is completely unbalanced. And in the best case, it can become log n when it is balanced. We are going to talk about self-balancing BSTs, which make sure that height never goes beyond order of log n. So in those cases, search becomes big O of log n. But when we talk about normal BST, height can be n. So we can say time complexity is big O of h only. We can't say it's big O of n or it's big O of log n because it can be anything. So big O of h is the best term to represent the search in a normal BST. But when you talk about self-balancing BSTs, which maintain their heights to be log n, we can call the search function as big O of log n.